Okay, we are very pleased to have Professor SungHa Kang to give this week's 1W-Minds seminar today. Dr. Kang received her PhD degree in applied mathematics from UCLA in 2002. She is currently a professor of mathematics with Georgia Tech. Before that, she was a tenure-track assistant professor with the University of Kentucky. Her research interests include mathematical approach to image processing, numerical methods, and scientific computing. Now, Dr. Kang has served as the academic editor for the Journal of Inverse Problem and Imaging and the Journal of Advances in Continuous and Discrete Models, Theory and Modern Application. Today, Dr. Kang will talk about identifying differential equation with numerical methods. Your turn, SungHa.
Thank you very much. I would like to thank the organizer for this opportunity. I am very honored. So hopefully this will be interesting to you. Okay, today I'm going to talk about identifying differential equations from a given data. So there is a number of work, the series of work we've been doing in this direction. So today, rather than focusing on one paper and then focusing on one, I want to sort of give an overview of the idea that what have been kind of driving in this field. So hopefully it will be more comprehensive overviewing talk that which have sort of a common thread to these approaches. So, and also I would like to shout out to my collaborators. I utterly appreciate all of the collaborations, all of the discussion. Wenjing Liao, Yingjae Liu, and also my previous student, Roy Wuchen Hee, and Namjun and Xiaoming, as well as Yajun. And also the Hao Liu at Hong Kong University, also Mengyi Tang, who was my former student, and Rachel. And this has been really productive. So hopefully I will be able to give sort of an overarching idea of the type of work we've been doing. So for the outline of this talk, that I'm going to give a brief introduction on some of the related work, mostly focus on some of the beginning work. And I will focus on first talking about the first method, the identifying differential equation using numerical technique, because this is sort of a backbone of the type of work that we've been doing. So I want to at least give a good motivation of this approach. And after that, we will show how we've been kind of making improvements in different ways in these different methods. And briefly, I will talk also about how we can handle the varying coefficient as well. Okay, so related work. So given a data, how to understand or how to have an idea of what is the underlying dynamic has been around for a long time. So meaning the concept of being interested in the dynamics, which gives us this phenomenon, has been around. But because we don't know anything about the underlying equation, it is sort of natural to think there is some sort of sparsity involved. So there is only maybe finite number of terms that which is contributing to this dynamic. So some of the early work is in 1970s, but some of the recent work is stemming from sort of a sparse regression. So one of the most well-known work in this area is Cindy, and then there's a lot of extension from it. And also there are some theoretical consideration and also some PDE based method and some weak form and weak Cindy and so on. So this is sort of the beginning part of it, but there's a really numerous citation, and then please feel free to some of our recent paper for the citation as well. I will mostly focus on ODE and PDE, but in identifying the equation can also be understood as an agent-based approach. So this interactive law, this shows how the agent-based, the interaction. So this is the type of work that looking for these kind of interactive law. And also there is some machine learning type approaches for finding PDE. There are many, many more. So the setup of the problem that I'm interested is this. given a one realization of the data. So in real life, let's say some interesting phenomena, interesting physical phenomena is happening, then you took a video of it. And what can we do with this one realization is our motivation. So it is not like we are going to have a training. We don't assume there's many data. Whatever you have, that's it. How far can we go with this one single realization is the direction that we're taking. So now when you have an observation, we have to assume there is some noise. In some of the early work in this direction, the noise was added in a very interesting way because noise is very difficult to deal with in this setting. So one of the theme that we're going to talk about is how to denoise this properly. Now, the underlying equation is what we're looking for. So UT is equal to F of something. This is the type of equation that we're looking for. And we assume in this paper, the noise is added. So U plus of a noise is the model that we're exploring. But this in general is so general and you don't know how this look like. So one easier way to handle this is assume that this F is a linear combination of various terms. But these terms can be nonlinear. You can have UXX multiply, UX square, something like that. So you can have a nonlinear term, but it can be expressed in terms of linear combination. Now, throughout this work, we've been very consistent on what sort of dictionary that we work with, meaning that we say, all right, we allow up to 2 multiple, we allow up to 6 multiple, we allow up to second derivative, or we allow up to 6 derivative, something like that. So we were very consistent and we do not pinpoint these feature terms, but we just decide, okay, up to second derivative, 2-term multiple or something like that. So once you decide this, the feature term can be made as a column. So UXT, this is the data that which is given. This is the only data which is given. And then every other term, you have to make it. So U square, you can just square them. UX, you have to take the derivative. You have to take the derivative and so on. So each and every term, you need to generate this from the given data, which is only U. And we are looking for a differential equation. So it needs to be fit to UT. UT is not given either. So UT is also approximated. So now if you set it up like this, it becomes a linear system. You have F, which has a feature term. And then A is the coefficient vector, A1, A2, A3, A4. And then B is our UT. So throughout this talk that I'm going to talk about support. When I say support is whatever is non-zero. So let's say everything is 0 and then only one term survives, and that is the support we're looking for, which is the 5th element. So that's a support. So if we find the correct support, that means we're finding the correct term which expresses the dynamic. After you have this term support, we still need to find the coefficient. Okay, so that's 2 different things. In this talk, I'm going to mostly focus on some numerical techniques to find this. We don't have any deep learning or network training. Like one single data, how far can we go with the method that we already know? And how concretely we can determine. So that's the idea of it. So let's talk about the first work. So this is sort of a backbone. That's why I'm showing you this. So given a discrete data, discrete data is given to us. Now we're going to make a feature matrix. As I explained, this AX is equal to B. You make the AX equal to B. Denoising is quite important in this work. So I am from imaging. So I still do imaging. This is my first love. So I have all the tricks and all of the technology to do denoising. But for the identifying differential equation, the order guarantee is important, meaning the underlying dynamics, like if it is a smooth function up to n-degree polynomial, can we recover this n-degree polynomial is important. So all of the denoising method that we use is something like a moving average least square and then fit up to second order polynomial, third order polynomial, and things like that. So the denoising method we use is the polynomial approximation based. Now, after you do this, so after you set it up, we're looking for the coefficient A. So the one part of it is to find the support, as I said. And then another part is finding the coefficient. So in order to find the support, how do you find the support? So one of the most simple, fundamental thing you can think of is a sparsity. So for the first work, we did the same thing. We did L1. We did lasso also. We did that. But when you do lasso, there is a lambda dependence. So in order to choose a lambda, there's some machine learning technique to find this lambda and so on and so forth. So it is not perfect by itself. So for the first work, we added a time evolution error to actually help us find it. So as I said, I want to give an overall, the overview of kind of direction and what is the fundamentally important thing in this identifying PDE. So this is what I can summarize. One aspect which is important is the setup. So how do you set up a linear system and what kind of denoising that you do is very important. After that, you need to find the support. You need to identify what is the right term. And then after the support is found, you find the coefficient by least square. So every three aspects of it, we're going to make improvement one after another. Okay, so now the denoising, as I said, we want to have some guarantee. So we guarantee that if the given data is sampled from, let's say, third order approximation to a smooth function, then the moving average least square should give us the same order so that even after the denoising, we're not losing the information. So that's why we are using it like that. So this is the outline of the IDENT. Given the time-dependent data, so you have a spatial and time-dependent data, so the different color represent different time. We use lasso, the L1 minimization. There's 1, 2, 3 term, which is non-zero. Usually the difficult part is how to find the threshold. So we don't deal with that. We just take all of the term, which is non-zero, but we refine it by using time evolution error. In this case, the true data was Berger's equation, so they should only have one term. But there are 3 terms, which is non-zero. So now what you do is using these 3 terms, make up all possible equations. ut is equal to constant, ut is equal to u, ut is equal to some ux, ut is equal to some constant plus the u term. And these coefficients are computed by least square. Okay. Now, what time evolution error does within this 7 equation, you evolve it. Use the initial condition, only the initial condition that you have. You evolve this with a smaller delta t. Smaller delta t is the key. Smaller delta t, and you evolve, and then see what happens at the end. And then you compare the difference. This is because L1 minimization itself is often not enough. And then the 0 or not, it is you cannot really say that this is 0 or not. So this is why we're adding with it. So from the initial condition, you have different possibility. The candidate equation, you evolve. You have a green one, you have a red one. The red one is really far. And then whatever is closer one that we pick. There's two fundamental idea behind time evolution. One is, whenever you do this kind of PD identification, if you can go to each feature, constant, are you in or out? And then you go to the next one, are you in or out? Yes and no, yes and no. If you can do it one by one, that would be great. But it doesn't work like that. It's a nonlinear PDE, so it has to work as a set of equation. So set of the equation has to work together to express this dynamic. So we really cannot say yes and no for each term one by one. You have to work as a set. And then when we do the evolution, we do a smaller delta t because this is the fundamental of numerical convergence, right? So the consistency and stability, if you have delta t and delta x goes to 0, it has to approach the underlying PDE. So this is the idea. We want to kind of see what is closer to what is given to us. However, this is slow, as you can imagine. You have to do with a small delta t. You have to evolve from initial condition to the end. So it is very slow. So in the case of robust ident, we started doing multi-shooting. So rather than doing the initial condition all the way to the end, we shoot from multiple location and then consider that to be the initial condition and evolve. And then you add all of these differences to find the best one. So this is a basic idea of multi-shooting that we utilize for that. So this is an experiment showing that as the noise level increases, that using the moving average least square denoising definitely helps to reduce the error. So having a denoising is important, and we can have some success. So for example, for the Burger's equation, up to 30% that you can kind of recover up to a certain accuracy. But if you have a same Burger's equation with a diffusion, for example, just a little bit of diffusion because it's a second order, it gets harder. It gets much trickier. So in this paper that we showed, that the error is dependent on that. So you have a noise level, because we're adding a noise, we have a noise level. If the underlying dynamic is really high degree, like, fourth order derivative, like fifth order derivative, then it's going to be much more challenging to find the underlying equation. Partially because we're using the difference, finite difference for it. So so this is one thing that we need to keep in mind. The noise as well as the degree, the order of the degree in the underlying PDE is important in the recovery. When we're using the L1 regularization, we do have an asymptotic theory showing that asymptotically, we can give the sufficient condition for the support recovery. But we do a little bit better than the support recovery, that we can find the correct sign as well. So this is a more statistical direction on it. Moving forward from this. Now, learning from this, we're going to move forward. How do we move forward? So we know the noise is challenging. So we denoised it properly by using the moving average least square. However, when you have a derivative, double derivative, triple derivative, whenever you have a derivative, it gets harder and harder. So in this paper, what we suggest is a successive denoised differentiation. So what it is, the given data, you denoise it. And then you consider the derivative because you approximation to UX. And then you need an approximation to UXX. You denoise this one more time and then do the differentiation. So you successfully do this. Okay? Another improvement that we made is the sparsity part. In order to find the correct support, we moved away from lasso or L1, but we did subspace pursuit. So subspace pursuit is a greedy algorithm. So what it does is that you need to give the sparsity. So for example, K is equal to 1, meaning among this F matrix, find the one column which gives you the best solution. What is the definition of best? Is the least residual error. Now, when K is equal to 2, find the 2 best column that which gives you the best solution. K is equal to 3, 3 best one. K is equal to 4, and so on. But so K has to be given. K is equal to 1, K is equal to 2, K is equal to 3, K is equal to 4. Otherwise, it's very concrete because you're looking for that number of column that which gives you the minimum residual error. But because you have, for different K, you have all these solutions. Among these K, you have to pick one. So among all Ks, you have to pick. So as I mentioned earlier, we use the multi-shooting time evolution. However, if you start using the subspace pursuit, it is more stable. It is much more stable. So even cross-validation works. Cross-validation is just you have a data, you are given data, you cut it in half, use the half to find the coefficient. Use that coefficient to fit the rest and then see how good the result is. So that's it. So that you do the cross-validation, it already gives a pretty good result. So coming back to the general theme, the overview of the idea, that you can say the same thing. Linear system, how you denoise it. So we do STD to denoise it. How to find the support. For each sparsity, you find the support. But because you have for each sparsity, we have to find the best support one more time. But subspace pursuit has been very stable. At the end, we just used a cross-validation was already pretty good. After the support is found, you do the coefficient identification by least square fit. But that's a bigger idea for it. We do have a theorem because we are doing denoising, differentiation, denoising, and differentiation. We need to have some sort of guarantee. So with some assumption, meaning polynomial of degree S is used for moving average least square. And then the step has been used. And then the finite difference method that we use has to be accuracy up to S minus 1. Then if you do successful denoising and differentiation, you can have a certain accuracy. So at least we can show there is some guarantee of the order recovery, even if you do SDD on this. So in this case, you have a discontinuity, still you can find it. You have like 30% noise, which looks like that, but still it recovers. The original equation is UT is equal to negative UX, and then you get negative 0.9 of it with a 30% noise. This is comparing the coefficient error, and then the error value is pretty small. We can do this for the Burger's equation with diffusion, for example. Before, maybe you were able to do only 0.5%, that you can go up to 5%. We can do it for the third order derivative as well. Now, how do we move forward from this? Now, we move forward with a weak ident, because around this time, there were some other work also using the weak form as well. So now, let's consider the weak form. What is the benefit of weak form? The weak form is integral of the test function, like that. So if you use the weak form, one of the beautiful part of it is the part of differentiation, the finite difference that which makes the derivative approximation very unstable with noise. This can sort of handle it much better because it's an integral form. And you can use the integration by part to change the model as well. So we explore using the weak form. But if you want to use a weak form, you need to use a good test function. So I will talk about what is the good test function that you need to use. We again use the subspace pursuit. But in this case, we do more than that. Because fundamentally, what we're looking for is the PDE underlying equation, differential equation. So, and we assume the data itself has noise. So you have noise in U, UX, UXX, all of these things. The effect of noise might be different. So we kind of normalize this. So you want to make sure the effect of noise is going to be similar per a column. So we error normalize for that because this is given. And also now we can even improve the least square fit. For the least square fit, rather than fitting the whole data, we can kind of focus it on an important region. So we even explore that. And then the SP. SP for every sparsity that you're looking for the best fit. But at the end, it's the least square fit. If you have least square fit with more terms, of course, the residual error is going to get smaller. So the more terms you have, the better it is. But the more terms, that may not affect, that will not give meaningful input to UT. So then we started trimming that part. So this is the trimming. And then we find the coefficient, and then among all K, we use cross-validation. Oh, sorry. Yes. So again, talking about the general form, now the linear system is generated with a weak form, and then the weak form gives the denoising. Now the support and coefficient identification is merged inside your SP now. And then at the end, we just pick the best one. So the coefficient identification got improved with a narrow fit as well. So there are four things that I want to mention in relation to this weak ident. First is the weak form. As I said, the benefit of weak form is the difference. So you have ut or uxx or something like that. Those kind of derivative can be moved to the test function. That's really is the beautiful part of this. So by integration by part, whatever the derivative that you have, you don't have to deal with u, because u is the one that we don't have. We only have a discrete value. But this test function, we can decide. So all of the derivative moves into the test function. That is really the beautiful part of this. But because of this, if you want to utilize the integration by part, your feature term has to be specific form. But most of the equation that people care about, meaning that in these kind of work, there's like KdV equation, Ks equation, all of these equations satisfy this particular equation. So that's why the weak form is powerful in this way. Now, in order to do this, number one important thing is the test function. What kind of test function? There's a fundamental idea, it needs to be continuous, right? Because we want to move all of the derivative to the test function. So the test function has to be nice, quote unquote nice. What does that mean? So we experiment this a lot. So initially we tried like p is equal to 2 is usually what people try. So 1 minus x with a square, right? Because this is smooth enough. So this is the thing that we try. So this one, shout out to Messenger and Bolt. What they did is they provide a way to design the test function. So what you do is given a data, your data is given, you consider the Fourier transform. So in the Fourier domain, you see the response. From this response, there's a meaningful region and then the noisy region, high frequency noisy region. You chop the noisy region to be noise, but you don't really chop it. You kind of suppress it so that it will be in a tail end of this polynomial. So this is sort of matched to the Gaussian and then matched to the 5% noise. That's where the noise should lie. So per different data given to you, then your P and M will be automatically computed. So this is really nice, very nice test function. At the end, what happens is that the P value can be very large. So the P is like 10 or something like that. So it's like really high degree polynomial. It's not like P is equal to 2. So some of the weak formulation that it doesn't work very well, then you might want to investigate the test function as well. The second part I want to mention is, as I said earlier, the noise. Per feature, you're going to have noise coming out from it because of the derivative, ux, uxx, or things like that. So because of this, we want to normalize it. You want to make sure all of the effect of noise will be sort of uniform. This can be computed. So you have a leading coefficient error. U plus epsilon is the noise. And then if you write it out, then you can explicitly write what is the leading coefficient. So this leading coefficient term is going to be normalizing the column so that the effect of the noise will be uniform around it. So the weak ident goes like this. You have an input data, which is in a weak form. So WB also is a weak form. And you use SP. Now in the SP, so K is equal to 1 or K is equal to 2, to fix K, you find the best support, but we further trim it. So the term which doesn't contribute to UT, we cut. And among the feature that you have, the right support, now when you fit to find the coefficient value, we only use the dynamic region, high dynamic region. So the third thing is the high dynamic region. Rather than fitting the data entirely, we're only going to fit in this yellow region. So the least square problem becomes much narrower because we're fitting only the meaningful one. So given a large data, when you're doing a least square fit, we are choosing to fit a better one. So the coefficient recovery actually becomes better. The fourth thing that I wanted to mention is trimming. As I said, we remove some of the trimming. This is the effect. So k is equal to 1 will find something, k is equal to 2 will find something, k is equal to 3, and so on. At some point, we don't really need 10 terms, 11 terms. So how do we get rid of it? But we get rid of it by contribution. Does the column that you have, including the coefficient, does this contribute to UT? If this is less than 5%, 0.05, then we remove it. Then quickly converges. So even if the sparsity is allowed to find 40, but they will actually fit, they will actually stop adding at some point. So because it's a least square fit, trimming is very efficient on that. So we compare with different methods. So we compare with the Wixin-D PDE, Wixin-D ODE, and also Grigoriev's group on the using the weak form, as well as the Cindy. We experiment on different equation. This is an example. For the experiment, especially for the comparison, we have taken the data from the paper, like because in PDE identification, it is subtle. If you have a different initial condition, it might work better than the other. So in order to be fair, we took the data which is used in the other paper to do the exact comparison to our method as well. So that at least the data will be equivalent. So this is the result. So this is an example of transport equation. So this is the true equation. And these are the recovery using 3 different methods. This is no noise. If there's no noise, lot of the method does relatively well. If you have 1, this is 100% noise. It's a very strong noise. Now, if you start using very heavy noise, the coefficient error for weak ident is 0.08. Others are bigger in a way. Some of the times they do not use the full dictionary. They use pinpoint on certain things, but we don't do that. We just do everything and we just do it blindly. And this is the recovery, the equation that we have. We did this statistically. So for different level of noise that we tried it 20, sometimes 50 times. And these are the plots. So this is sort of the L2 error for the coefficient. And this is true positive or false positive. So this has to be equal to 1. So there are some outliers. But if you use a weak Cindy, then there is more variation, for example. We have compared to all different methods, but the weak Cindy was the best among. So this is why we just show the comparison with the weak PDE for this page. We can do this for reaction diffusion, which is a system of equation with a double derivative and nonlinear terms. And then this is the recovery. It looks very messy. However, if you look at the coefficient error, it is 0.03. So it is very, very accurate. We also apply this to ODE. For our purposes, we find ODE to be easier because it's not PDE. So meaning that you don't have like derivative, spatial derivative. So even if like we have a Lorentz equation and all of the equation, more or less the result was quite stable. So because I know there are a lot of interest in the solving the ODE, the dynamical problem, like a Lorentz system and so on. So I do want to mention that it works. So the red dot is the given noisy data, and then the black is the true dynamic, and then the black is true, the red is only given one, and green is what we identify. So the green is very close to the black, so close to the black, and also for the Lorentz system that it is quite accurate. And these shows the coefficient error from that. Okay, so how do we go further from this? So so this is just the statistical plot with the weak ODE and Cindy. We compare to the Cindy because this is a dynamical system. So in ODE that we compare with that. So this is the error, L2 error showing, and then the true positive and false positive. So it is more accurate. Okay, so how do we go further from this? In the weak ident, one of the interesting part is that we started looking at the frequency domain. So we take the Fourier domain first to get the test function and so on. So we thought, okay, how about we use the Fourier domain? Because the Fourier analysis is a really important part of understanding PDE as well as numerical PDE. So we wanted to see if there's any relation to that. And some theoretical work on the Fourier, the frequency versus their identification. There's some work on that as well. So what we do is that we take the discrete Fourier system. So given an image, we take the discrete Fourier transformation and make a system out of this. Now, when we make a system, we look at the Fourier domain, the frequency domain. There are noise. So how do we know which one is noise? So we follow the theory of Fourier analysis that if you have a smooth enough function, the decay rate of the coefficient has to be 1/k. So then after that, everything else, we define this to be noise. So we first, we cut the domain, the large frequency domain, to sort of a meaningful region. But even then, we do more than that. Essentially, what is important is UT, how this dynamic is changing. So the response of UT, we pay attention to the response of UT in the frequency domain where you have a high response for UT. And using that as a region, and then we do subspace pursuit on that. So all of this computation is done in the frequency domain. And we do the trimming. So we went step 4, so we do group trimming. But the idea is that, but the difference is that we're working in the frequency domain. And because of the magnitude difference, it is very challenging to do. So we started partitioning the domain to consider the meaningful region, and that really helped. So now we get the optimal sparsity by considering the union of this meaningful region, and then find the coefficient on that. So overall idea, linear system in the frequency domain. Denoising is done by test function as well as the frequency domain partition. And then the sparsity is enforced inside this partitioned region. So the frequency partitioned region. And then the best support is also found in this region. So this is the setup of the Fourier, discrete Fourier transform, how the system will look like. So all of the entry is to find a discrete Fourier transform, and then B also UT. This theorem shows you the error analysis. So initial work that I showed you, if you have an underlying dynamic, which is a high order, like it's really like 5th order derivative and so on, it is very difficult because the error increases. However, if you use Fourier type and even the weak form also, the error is linearly dependent. So there is an epsilon here and there's an epsilon here. So this is why if you use sort of a weak form, that you have a better recovery because you have a better control, you have a better chance to controlling the error for that. So the Fourier ident goes like this. K is equal to 1. SP with K is equal to 1 found 1 support. K is equal to 2 found 2 support. K is equal to 3 finds 3 support. K is equal to 4 found 4 support. But one of them is really not contributing to UT. So we cut. So he left with 3 support. In K is equal to 5 again. So as you can see, it already converged to having the 3 same support from it. After this support is found, so this is UT and then 1, 2, 3 of them, then you find the coefficient which is meaningful. So now you find the coefficient and find the smallest residual error, and this is the recovered equation for that. So this graph here is showing the reduction. So if you have an entire frequency domain, and then if you find the meaningful region, meaningful meaning in the Fourier transform, the theory of Fourier, the smoothness will give you the decay. So if you follow the decay, this is the only meaningful region. So that part is zoomed in here. Within here, only the activated term, which is high response, this white part is actually used in computing the least square. So these are sort of the meaningful data, which is already denoised. So denoised by frequency partition, but also by the test function. Okay, so this is a comparison. So Fourier ident, weak ident, and weak Cindy. More or less the result is very comparable. So Fourier ident can be good. But also, for example, weak SIND and weak ident can be comparable sometimes. So more or less, this is a very stable, good method. One of the best part of using Fourier ident is that if you have many modes, many frequency mode in the data itself is very, very complicated. Then even if you have a high level of noise, so this is increasing noise, the Fourier ident seem to do much better. So this is the coefficient recovery. So the weak ident is already good, but it is even better than the weak ident. So this is the interesting part of it is that if you have a lot of frequency mode, that Fourier ident can do much better. So up to now, just to summarize what I've been talking about is if given a single set of time-dependent noisy data, we can actually do something. So noise makes it challenging. Higher order derivative makes it challenging. However, if you can decide on the linear system in a proper way, denoise in a proper way, and then find the support in a proper way, and then even the coefficient identification, we can even do better. Least square was used. Now you can do high dynamic region or smaller meaningful region. Then even the coefficient recovery can be better. So if somebody asked me right now, what is the method that I want to use? I don't care about any of this. I just want a method and I just want to do it, try for my data. Then I would recommend using weak ident. So we have a GitHub available, the code is available. I would recommend using the weak ident because it is stable. However, why do I talk about the ident and robust ident? The reason is the weak ident and Fourier ident, in order to really make use of it, the integration by part has to be used, meaning some of the term is sort of restricted to take the full advantage of the weak ident. So in the finite difference, yes, finite difference is difficult. You need to have a denoising in a proper way, but you can have many different types of equation. You're not restricted by integration by part in a way. And then the boundary condition can be free as well. So in the weak ident, we did adjust the boundary, meaning you have a boundary condition which is non-periodic. We pad it. So we don't change the boundary condition, but we make sure we pad it to make it periodic. So these are some of the difference in between these methods. So one final thing that I want to briefly mention is on varying coefficient. Up to now, I'm trying to find one equation representing this whole dynamic. But maybe dynamic is changing. So how do you deal with that? So for example, like this. You have a certain dynamic. Let's say at the beginning, it started out being a heat equation, but then it changed to Berger's equation or something like that. So then how do you deal with these coefficient, which is changing? So already the identifying differential equation is challenging. There's noise, there's high derivative, and so on and so forth. But this is even more challenging because you have to have more variation. You're allowing more. So one of the common setup of this is to use the basis function. So finite element method, like a finite element. So you have an element. So you approximate the coefficient by these elements. So in the initial paper of our ident, we also had this. So I want to briefly mention. So following the overarching idea that I've been talking about, so you have a linear system that we need to do. Now, because we have a base element, finite element everywhere, the matrix gets fatter because every single element that you have, they need to have a point giving us a value. So the feature matrix, this has to be much triple like or L times, depending on how many of your elements that you're using. So the matrix itself, this linear system is really big. For the first paper, because we use lasso, in this case, we use group lasso to do it. But group lasso, the identification of the support is not trivial. So how do you know which one is a meaningful support? So in this case, we increase the number of elements. So we call this base element expansion. This idea is also using the convergence of finite element approximation. So you have more elements to approximate, the better the result that you're going to get. So if you increase the number of elements, whatever is stable is the true term that we need to keep. So this is what we did for the initial ident. Linear system, denoising, we did by moving every the least square. Support identification using the group lasso. And then support needs to be refined, and then coefficient needs to be found by having the L extension. We move forward from this. Now we move forward. So we have a similar setup of basis element. So you have the finite element to represent, but the denoising is done by STD, right? The extension from the robust ident. We have an STD, and then now we use group subspace pursuit for that. Even after this, we need a way to find which one is the right sparsity. So we do the reduction in residual. Okay, so this is consistent theme. The group SP that we propose in this paper is different from block subspace pursuit. So the group projected subspace pursuit, the main difference is that when you're looking for the column, that we are compared against to the column space of the previous vectors. So that is the difference. But if you use the block subspace pursuit, you just find the best one. But we do project to the column space. So this is the group SP. So you have a feature matrix which is much thicker because of the number of elements that we have. And then we use the group SP, k is equal to 1 to k max. And then among this k, we find this by the biggest drop, the first drop that you have. And then we do a least square fit. So this is the result. So this is the true dynamic. This is the true dynamic, which is moving. And then if you use a group ident, then this is the error. So this is the absolute error. So it is mostly blue, meaning that it is very close to 0. And then this is no noise. And then if you have 2% noise, then there are some spots that which is not as accurate. And then some of the coefficient also. But this is the general behavior that you can observe. We did compare with the group lasso as well as the Cindy, one of the Cindy, as well as the block SP. Some of this method is not utilized for identifying differential equation, but just as a comparison of the method that we still compared it with a similar idea. So just one result I can show, I mean, the paper is already published, so you can find more results. Using the different method, that the true solution has 3 terms. So independent to what dictionary that we use, the reason is some of the time, because you have so many parameters now, because you have the finite, all of the elements, as well as all of this data is really very heavy. Some of the method required to have a smaller dictionary. So, but we didn't want to do that. So one dictionary has a small number, the second one is bigger, the other one has like 300 features. But all of the dictionary, whatever that we use, find more stable result. In this example, the BSP also, the block subspace pursuit also give relatively a stable result as well. Okay, so just to summarize, so I've been talking about how, given a single set of time-dependent, discrete, noisy data, how to find the underlying dynamic. So we use numerical approximation, finite difference, a weak form, and use the sparsity in a good way, and try to use the least square fit in a good way to identify the PDE. So right now, I would say weak ident is pretty stable. You can play around with it. You can handle high level of noise, and we've been progressing so that the identification will be more accurate. Okay, thank you for your attention. And this is the reference. Thank you.